Guys, welcome to another lecture from Ecopoint. And today I'm starting off with our new series, the series on linear algebra. So in today's lecture, we will try to understand what exactly is linear algebra. Let's today understand intuitively what linear algebra actually means and what we are actually doing. How come it is so important in so many fields? Be it data analytics, be it artificial intelligence, be it economics, be it physics, so many places this subject is used. If I have to put it in simple layman terms, linear algebra is the theory around lines and planes, but in any dimension, not just 2 dimension, 3 dimension, but even beyond that. Now, wherever you have lines, you have planes, you have equations. And wherever there are equations, you want to look out for solutions to find for those given equations. What variables, what values satisfy those equations, right? So think of linear algebra as a way to solve system of equations and more elegantly. That's what linear algebra is all about. If you want to understand it graphically, we are dealing with lines. What is a line? If you consider any linear equation, for example, what I have here is y equals to 2x plus 1. This is called a linear equation in two variables because we have two variables here. One is y, one is x. This graphically represents a line. This is the line y equals to 2x plus 1. How do you graph it? It's very simple. What you need to do is, how do you actually graph it? Just give certain values to x and attain y, which is 2x plus 1, and then plot a graph. If you take any point on this line, it is satisfying this equation. Any point on this line satisfies this equation. So all the points that you see on the line are solutions to this equation. Because they're solving this equation, they are giving you y is actually equal to 2x plus 1, right? Now, let's add another line to it. Suppose we add another line, y equals to 2x minus 2. Give values to x, attain values for y, and you can graph it. And you can generate this graph like this. What do you see here? What you see here is that these two graphs are actually intersecting because I drew them on the same graph, on the same plane. So they are intersecting with each other, right? This point of intersection is called a solution. This point of intersection is a solution. And what you see here is just one solution, just one point satisfying both the equations. So what is this point doing? It is satisfying both the equations at the same time. It's a solution to this system of equations wherein the system consists of these two equations. Now, graphically, you've seen this. But it would have been very easy for me to get rid of this graph, not think graphically, but just use algebra and solve it. When I say intersection, so both are meeting at some point, right? So at this point, the values will be equal for x, y. The values will be same x, same y, satisfying both the equations. So that means we can actually use algebra to find this solution. And it would have been simpler. I would have just equated these two. You can just get x minus 2 is equal to 2x plus 1 and solve this. Solving this, you will get x is equal to minus 3, y is equal to minus 5 graphically. Also, if you see, yes, that's what is happening. Y minus 5, x minus 3. That's the point where these two lines are intersecting. And this is your unique solution. Now, similarly, you can have equations in 3 variables. Suppose we have x, y, z in an equation. Now, that will give you a plane. It is no longer a line, but it will be a plane. What if you have three equations and three variables? That means you'll have three planes. If you have three equations and three variables, you will have three planes, which is now difficult to draw. But still, let's get some idea. So what you see in the picture out here, these are lines intersecting. And what you see here, these are planes. Planes are represented by three variable equations. These are planes. Yes, somewhere you can see that two planes are intersecting with each other. Somewhere you are seeing that they're not intersecting with each other. When you have more variables, more equations in the picture, it is difficult to graph them. And hence we use algebra. That's what linear algebra is all about. That is why it is for you to understand that linear algebra, first of all, is nothing but it's the theory behind solving equations. That's the reason what you will see here is a lot of vectors, the theory behind entire vector spaces and matrices. So why do you see all this? Because you have many variables, many equations. Ultimately, you're actually just trying to solve. In this video, I would like you to give a small picture of what solutions are like. Two variables, three variables, both the cases. First, let's start with the two variable case. So what are solutions? Solutions are point of intersection. You can have a unique one. Maybe you can have a lot of them. Maybe there is no intersection happening. So let's see what's happening. When you have just one single intersection point, that is your unique solution. It may so happen that two lines, two equations that you have, they're just going parallelly. They are not meeting anywhere. No meeting point means no solution. They are not meeting anywhere. So no solution is this scenario. Very easy to see graphically when it is two variable case because the graphs are simple. It's just lines. It's very simple. When you have a situation, for example, suppose you have x plus y is equal to 1 and 2x plus 2y is equal to 2. If you observe, when you create a graph for this one and for this one, it's going to be the same. What you see here is nothing but x plus y equals to 1 because 2 just turns out to be common. Or in other words, it's just twice of the first equation that you have. So graphically, it's going to be exactly the same graphs. That is why it's just one line out here. If it is just one line, that means all the x and y's on this line are satisfying these two equations. How many x and y's are there on this line? Infinitely many. Hence, this is the situation for infinitely many solutions. So simple when it is just lines. The moment you talk in terms of three variables, it becomes tedious to graph and see. But still, we will get some visualization today to these. Two equations in three variables. Just imagine if you have two equations in three variables. Suppose this is what you get after graphing. If you observe what's happening, there are two planes. So one equation in three variables will look like this one plane, okay? So this is like one plane. This is one equation in three variables. This is another plane. If you observe what's happening here, they are cutting each other, right? That means they are intersecting and they're intersecting. Do you think they can ever intersect on a point? Well, let me come back to this. But what you see here is they're intersecting on a line, right? This entire line is common. Okay, what you can do is you can probably take two cardboards and, one on two, put inside the other. You will realize what's happening. There's just one line where they are intersecting, complete line. Do you think they can intersect at just one point? Well, no, that's not possible. Whenever you have just two equations in three variables, if they are intersecting at all, if there is a solution at all, it has to be an infinitely many solution because it's a line. And a line basically means infinitely many solutions. If they intersect in a line, and therefore only infinitely many solutions or no solution is possible. But unique solution is not possible. In this scenario, unique, not possible. But what is the scenario? When I have just taken two equations, time and again, I'm emphasizing on the fact that I've taken two equations in three variables, then you can't have a unique solution. But what if I have three equations in three variables? Imagine a third plane. Suppose you have one base plane and then you also have another plane. And now imagine a third plane. Suppose, let's just take this picture into consideration and now add another plane to it, which is this, as you can see. If I do that, what do you see here? This plane, the new plane, is intersecting the base plane. Let's call this dark purple one the base plane. And on one line, it is intersecting it, but it's not intersecting the other plane. The other plane also intersects the base plane, but both of them are not intersecting each other. So if I am considering three equations in three variables, in this picture, what I see, there is no point that lies on all three of them. So that means there is a situation of no solution because there is no x and y, x, y, and z. No x, y, z satisfies all the three equations at the same time. Okay? So yes, no solution is possible, which was possible when I took two equations also in three variables, right? It's possible even when I take three. But think of another situation where we have three variables, three equations. And the picture looks something of this sort. So this time, the pink plane is not cutting like parallelly to one, but it is cutting in a manner that it is cutting the dark purple one also and the light one also. So do you think we can have a unique solution? Do you think it's a line where they all are intersecting together? No, it will just be a point. Think of it as like three cardboards with you. And if you see all the three of them touching each other, there will be a point somewhere in between, inside, that whole scenario. So there will be some point there. So yes, you can have a unique solution when you have three variables and three equations with you. Can you have any other situation? The other situation that we are left with is the infinitely many. Do you think we can have infinitely many solutions? Absolutely. If you take three cardboards like this, that there is one single line, entire line, which is common in all three of them, which is the most easy way to actually practically see with cardboards. This will be the most easy way to put in, fit the three cardboards into each other. Well, there will be an entire line. The answer is yes for infinitely many solutions. Now, why infinitely many solutions here? For a simple reason, there is one line, entire line, and there are infinitely many points that satisfy a particular line. Now, these were the scenarios where I could give you this visualization. And, I hope I've been successful at that. So now you have a visualization to solutions, to intersections of not just lines, but planes also. But we were just in three variable case, right? What if we have an equation which consists of four variables? What if we have four equations in four variables? Well, it becomes very difficult to deal geometrically, to deal graphically when it comes to so many variables. And that is why we need algebra. That's the thing linear algebra is dealing with. All the concepts that you will learn with me in linear algebra, ultimately, we will be solving equations. Okay? So keep that in your mind. One additional thing that I would like you guys to know is that when you have any equation in more than three variables, when it is three variable equation, what you get is a plane. When it is any equation in more than three variables, say, for example, what I have here on the screen is an equation in four variable. These equations are called hyperplanes. What we generate is called, that's called hyperplanes. Okay. I'll stop here for today and we will start working on the core of linear algebra from the next class. Thank you very much.